Good morning. It's your boy. We've talked about diffuse lighting and ambient lighting, which are two ways to approximate, lighting in our scene. I used to take breakfast though, excuse me. So we don't really have a good way to describe how lighting interacts with the surface right now. We have diffuse lighting, which is, kind of uniform across all surfaces. That's more it's more of a property of the light source rather than the surface. So two ways we can describe a surface in our model would be roughness, roughness, and reflection, reflectiveness. So those are two ways of describing a surface. It's very complicated in real life, but in our model, we can sort of combine these two properties into something called specular lighting. Specular lighting. So how does that work? Well, with specular lighting, we are sort of we are saying that there are two types of light. There's light that gets sent from the surface, from the source. And when it hits the surface, it gets scattered. So it sort of flies everywhere. And that's the diffuse light. So it gets absorbed by the material and then, emitted into the environment. But we're going to say that a little bit of the light also gets reflected off the surface. So even though, like a mirror, as it hits the surface, it directly bounces off and hits, our eye here. Here's our eye. That's a good eye. All right, so a little bit of the light directly reflects off the surface and hits our eyeball, as well as the light getting scattered everywhere. And this is called specular lighting in our model. This is not very real life equivalent. In real life, light is way more complicated, but this is how we're going to roughly approximate this behavior of light on materials. So now with this, we can define two different variables. We can define how reflective is it. We can define how much light is actually getting reflected off of the surface. So, if we have a mirror, then, 100% of the light is getting reflected. But if we're talking about maybe metal or plastic or something like that, that reflectiveness is going to go down to something like maybe cloth, where it's not very reflective at all. It's almost nothing. And we can also talk about how spread out the reflections are. So, here we have one focused beam of reflection. So this would be like, the very shallow angle of reflection. But then we can spread that out. We can say that, okay, the reflection actually goes out a little bit. And this will describe the roughness of the surface. Because if the surface is sort of, lumpy and bumpy like this, as the light is hitting it, this would be cloth or something, then, it's going to hit the surface a little bit different everywhere. So, maybe at some point here, it's going to reflect this way, and then at here, it's going to reflect it that way. And it's going to reflect, in all of these different angles, because the surface is very rough. While if the surface is completely smooth, like a sheet of metal or something, then it's going to have a very shallow reflection angle. So that's how specular lighting can describe roughness and reflectiveness in a surface. Cool. So how does it work? Or how will we implement, rather? So we're going to start with a quite simple implementation. Whoops, move this a little bit. We're going to start with quite a simple implementation where we take the eye position and we take, so we're going to look at, you know, the specularity of a single point. So let's talk about this point here, for example. It's going to be a 1 pixel. We're going to take the direction from that pixel to the eye location. So we're going to get that as a normal, and we call that E. As a vector, I should say, not as a normal. So it's going to have E, and it's going to be our direction towards the eye. And then we're going to have our light direction. So that's going to come in from, you know, here somewhere. Oops. That's going to be our light normal. I don't know why I keep saying normal. I mean light vector. So what we're going to do is that we're going to reflect our light vector. We're going to see, okay, how is this light reflected on the surface? So we're going to reflect it. So that's going to give us, you know, okay, I'm running out of space here. I'm just going to draw over here. We're going to get some sort of vector like this. That's our reflection vector. And that's, you know, the angle here. The angle of reflection is equal to the angle of, I think it's incidence. I remember. I'm not a physics. I'm not a physics. So these two angles are going to be the same. So we're going to get the light. We're going to reflect it to get the reflection vector. And then we're going to compare our reflection vector to our eye vector. So the more they are lined up, the higher the specularity, the more we're looking sort of directly at the light in the reflection. And the more the E and the R vector are diverging, the less specular light we're going to see. So we're just going to dot these two. So we're going to dot the E and R to get our specularity. All right. Cool. So let's do this. I was testing it out before. Okay, so first of all, we gotta get our eye position in here, because we gotta know what the eye vector is. So I'm gonna add our uniform. This is gonna be UI position. So that's gonna be our camera. So I'll add it to the render data struct here. So just add our glm vec3 eye position, like so, and then when we draw, I'll just send that into the material. Cool. And then I will also set it, because I didn't do that now. So I'll just do render data. Eye position is equal to cam position. So now we should have, it compiles, great. So now we have our eye position in here. So first of all, let's get the direction to the eyeball then. So I'll do, let's see. Specular Light. So I'll get our eye direction, and that's gonna be UI position minus, oh, we need the world location. Okay, so I'm gonna send that in as input then from the vertex shader. So I'll do f world. So that's gonna be our world position of this pixel. So I'll just go into our light vertex shader. See, and I'll add that as an output world, and then that's gonna be the position of the vertex multiplied by the world or by the model matrix. So we're, you know, transforming the position from mesh space into world space. So I'll do u model times vec4 a position. Whoops. 1, and then same thing like with the normal, we want it as a vec3, so I'm just gonna do the XYZ on that. So we convert it to a vector 3, and of course it does compile, so let's see why. On line 30, we're implicitly casting from vec4 to vec3 in the light frag. Okay, so let's check out the light frag. Line 30. Oh, right, okay, I just left a dangling minus minus sign there. That's not good. Okay, so we have the F world, so I'm just gonna do a minus F world. And then I'll normalize that. So now I'm getting the vector from the world position of the pixel to the eyeball, and then I'm normalizing it, so that will give us the direction to the eyeball. Then I'll get the reflection. I'll do light reflection, and as I'm going to use the reflect function. So the reflect will, you know, take a direction and then reflect it onto of a surface, and it takes a normal to describe that surface. So in this case, we're just gonna give it the normal of the surface that we're working with. So I'll reflect U directional light with the F normal. So now we should have the reflected light. Okay, so it compiles. Good. So now we have the light reflection. So now we have the two vectors that we're working with. So now let's dot it. So I'll do float specular is equal to dot I dir and light reflection. Like so, and then let's set the color to be only specular for now so we can see it. Let's see. Okay. So it kind of works, but it's quite... Get this kind of like Fresnel effect. This looks pretty cool, actually. All right, so yeah, you can see it's kind of working, but it's quite like it's not really. I mean, it's huge, right? Like almost the whole surface of the sphere is covered in the specular, while we want kind of a small dot. So here's where we talk about how we define reflectiveness. How do we make something more or less? Or rather, roughness. It's what we're going to talk about. How do we make something more or less rough? Because now this might be seen as just very unrough, I guess, but we want to make it rougher. And the way we do that is to talk about the drop-off of the reflection. Right now we have something looks like maybe a bit more linear like this. It's not actually linear, it's a little bit curved, but not very curved, something like this maybe. Like so. So we have, you know, as the dot product is 1, we're getting, you know, 1 specularity. So this would be the dot product. Dot. And this is the spec. And, you know, as we reach, you know, 0.5 dot, we're getting 0.5. That is actually is linear. We're getting like 0.5 specularity. But if we want something to be more focused, we want it to be like, you know, very shiny in the middle, but then drop off very rapidly if it isn't very rough. So if, you know, if the specular reflection is very focused, we want it to drop off very early. So we want a curve that maybe looks a little bit more like this. So, you know, very shiny when we're looking, you know, directly at the reflection, but then it quickly drops off as we're moving away from that reflection vector. So the way we can do this is to raise the specularity to some exponent. So I'm just going to raise it to some exponent. And the higher the exponent, the quicker it will drop off. So, you know, we might have a really high exponent do something like this. And if we do a lower exponent, it will drop off slower. So we'll have a more smooth linear curve. And that will mean it looks like a rougher surface. So let's try that. I'm just gonna const it for now. So we'll do a spec exponent, and we'll set that to maybe 64. That's probably a good exponent. You want it to be rough, pretty high. So I'll do specular is equal to pow. So that's the power function, and we raise it to specular. We'll raise it to spec exponent, like so. So let's see. All right, so now we have a more focused dot where the specularity is, and if I get here, like there's, now we can see we are directly aligned with the vector, and then as I move away, it fades, you know. Now this would be, you know, quite a focused specular surface. A very smooth surface. This might be maybe metal or something. So then we can maybe smooth it out a little bit, maybe do 32 or something. So now the dot is a little bit bigger. So now the surface we're looking at is perhaps, you know, a little bit rougher. Maybe we're looking at plastic or something. And then we can go even lower, maybe 8 or something. And now it's very spread out. And then if we spread out even more, we might be looking at like cloth or something. If we do 2, like cloth being very rough. All right. Okay. Yeah. So why is this happening? What's happening here? Well, that's because as we're looking under the object here, this dot product, right here, this dot product is actually going to turn negative as we're looking behind the thing. So we have to make sure that we ignore negative specularity. We don't count that. So I'm actually gonna specular is equal to, I'm actually gonna do a max of that. So the specular 0. So that will make sure that it's never goes below 0. So now if I look behind it, it should be black. Yeah, there we go. So now we're looking at a very very rough surface. The specularity is very spread out, and of course this doesn't look very real. So in reality, if we're looking at cloth, it will be more spread out, but of course it will also be, you know, since it's more spread out, it shouldn't be this bright either. So I'm actually gonna do a spec intensity as well. So in the case of cloth, it will probably be pretty low. So I'll do that. So that's going to be equal to that times spec intensity. Since the light is spreading out more, we're also expecting it to be, there we go. Now this looks a little bit more like it would be like a clothy surface or something. If only it wasn't because it's pitch black. Also like this like Fresnel effect. This looks pretty cool. Sweet. So that's specularity, and that's one way to model specularity. Let's look at it on a little bit of a bigger surface. I'm actually going to make a floor for us just to look at the specularity on something a bit bigger. So I'm just going to make a, I'm going to draw the cube again. I'm going to translate it downwards and make it bigger. So I'm just going to scale it. I'm gonna scale it a lot actually. Let's do 25. And you know, I usually say don't scale non-uniformly. I'm obviously not gonna care this time. It's fine. Since it's a cube, it won't mess with the normals anyways. But yeah, this is technically, you know, we might get weird stuff if we're not careful. Okay, so there it is. And you know, it looks okay. It doesn't really look great. It's like a perfect circle, which looks kind of weird. Let's actually up the exponent a little bit again. Let's up the exponent to 32 and up the intensity a bit. There we go. So it looks okay, but it's like a perfect circle. It doesn't look great. If I'm, you know, if I'm looking down here, then you know, I'm expecting it to look a little bit different. There are also some other limitations to this that is kind of hard to see on a directional light. But I'm gonna show you another way to calculate the specularity of a surface, and that's called the Blin-Phong method. So let's draw that. Let's see, I need a little bit more space, I think. Let's do this. So we're going to look at the Blin-Phong method. So the Blindfold method is trying to capture the same behavior, but it does it slightly differently. So if I have the surface, I'm going to draw a little bit bigger this time. So here we have the eyeball. Looking at it very intensely. So we have the eye vector here. That's the eye. That's the direction to the eye. And then we have the light. So this is L. What the Blin-Phong method does is get the middle point between these two vectors. So you get sort of the middle here. That's going to be the middle. So it gets the middle point between the two vectors. So you know that this angle is equal to this angle. And then what it does, instead of dotting the reflection with the eye, it dots the middle vector with the normal. So if this is the normal, I'm drawing a little bit slanted here so you can see it. It instead compares the middle point of the eye and the light vector to the normal. And that gives it a slightly different result than just comparing the eye with the reflection. It actually gives it a little bit more of a complex behavior that looks a little bit more real and you know, not as artificial. So let's try that. So we're gonna calculate this middle. Oh, excuse me. We're gonna calculate this middle vector. So if we how do we do that? Well, if we have the I vector E and we have the L, then if we could flip the L vector, so the L vector is instead pointing away, so you know, towards the light, then we would have this situation. So we have E and then we have L. Minus L. And then if we add these two together, then you know we'll get this plus this. I'll add this here. Like so. And that will actually always give us, you know, sort of the middle point, the halfway point between the two vectors. Assuming they're pointing in roughly different directions. And then if we just normalize this, we'll get the normalized the normalized middle point between the two vectors. So we're gonna add the I vector to the negative L vector. So that's what we're gonna do to get the middle point. So let's do that. So I'll go back and let's go using Blin, Phong, baby. So we get the I direction, we still want that. We don't want the reflection anymore. So instead we're gonna get the middle. And that's gonna be normalized I dir plus minus U directional light. And of course, plus minus, we could just do minus to get the same thing. But you know, it looks a bit clearer, I think, to do this, what we're actually doing. So that will give us the middle. And then instead of dotting the I there with the light reflection, then we dot the I there with the middle. I left a 2 in there. There we go. So let's see what happens now. Okay. I seem to have messed something up. Doesn't look right. Oh, right, no, okay, of course, I fucked up. We're not supposed to compare I there with the middle. We're supposed to compare middle with the normal. That's what we're supposed to do. So I'm gonna dot that with the normal. There we go. Okay, now this looks a little bit lower, like I expect. And now you can see that we're not getting a circular, we're getting more of a elongated specularity like this. And this is more what we expect to see in real life. You know, if you're looking at the horizon in the ocean, you can sort of see a line of specularity going upwards. So this is more reflecting of what we see in real life. the behavior, you know, as we go around like this, we don't get the halo anymore. We more get, you know, a dot like we expect. So this is the Blindfold method, which is, you know, the more commonly used method by far, I would say. It doesn't only have the fact that it sort of models how light actually behaves a little bit better. There also are some limitations to the regular Phong lighting. I think this is the one we did, the regular Phong lighting. This is using a point light, so it's much easier to see this. It's much easier to see, or rather, this limitations comes from point lights. We don't have point lights right now, but if we had, we would get this ugly line going from around here if we use the regular reflection method. So you see how there's this edge here to the specularity, and that's sort of what happens with the regular reflection specular model. But with the Blin-Phong model, it's more smoothly evens out. So of course this has a very low exponent. I don't think it has, so it has an exponent of 0.5, which is, you know, not an exponent you're gonna see, but still it does highlight this problem. And also you can see here with the reflection method, you get this spherical almost. It's a little bit of a ray, but here with the Blin-Phong, you can see you get a much more clearer ray-like structure, which looks a little bit more real. Cool. So that's specularity. So now we've actually done the 3 important parts of our lighting model. And this, again, is the very basic, very easy to make. Oh, of course, we haven't even combined them yet. Oh, I'm so dumb. We're not done. So I'll just add the specular here at the end. Ah, there we go. Okay, so now we have all of the light combined into one. Ah, look at our beautiful scene. It's perfect. So no, we should probably throw back some textures at this at some point. But yeah, so this is the, you know, the very, very, very basic lighting model that's been done for ages and ages and ages. That was the first lighting model. No, probably not the first, but the first gaming lighting model that made popular. But of course, as you might know, this very quickly got, as soon as PBR became a thing, you know, we haven't really looked back since. PBR is pretty much, you know, expected in game engines these days, because PBR more realistically simulates how surfaces work, how light work with different surfaces by looking at, you know, how light interacts at a more deeper, real physical level. So you will define surfaces more on characteristics of the material, you know, hardness and stuff like that, rather than just like, oh, the only thing we have to tweak is the specularity and the specularity exponent. So very limited, not very realistic, but you know, it looks okay. It's good enough, I would say, for our purposes, and it's a good intro to how they work with lights and surfaces based on normals and so on, the rough mathematics. Cool. So that's light. So that looks pretty good, and I think next time we're gonna start looking at point lights to get some of that going. So see you then.